I'm going to tell you something new about model-based IO. This is joint work with Nan, Akshay, Alec, and John. All right, so let's skip motivation. Let's just dive into the definition. So we consider Markov decision process here. So in this game, you have two components, an agent and an environment. So the agent looks at the state of the environment and picks an action and sends to the environment, right? And then the environment basically reveals some information. It sends an immediate one-step reward back to the agent, and it also reveals the next state, which is sampled from the underlying unknown Markovian transition model. Okay? So this process goes on for H many steps, and the goal of the agent is to find some policy that maximizes the expected total reward across this H many steps. Okay? So let's take a look at the progress that we have in theoretical reinforcement learning side. Okay? So today we understand how to solve this small discrete tabular MDPs very well. MDPs that contains finite number of states, finite number of actions, and a horizon. Right? So we know that there are algorithms that can achieve absolute near optimal policy by just interacting with polynomial number of times with the environment, poly with respect to number of states, actions, and a horizon. Okay? But one potential issue here is this poly dependency on the number of states, right? So this probably going to forbid us to transfer these algorithms to solving large scale problems. For instance, problem like Go, where we know the total number of states is bigger than total number of atoms in this universe, right? And it would be really nice if we can use something like function approximation techniques, right? So that we can get generalization ability, in a sense that we can make a reasonably good prediction even on states that we probably have never seen during the training time. And it would be nice if we could actually replace this, this poly dependency on the number of states by something like, VC dimension, or in general, some statistical complexity of my function class. Okay? Now, there's some previous work on general packed reinforcement learning with general function approximation. For instance, contextual bandits, which you can think about them as a reinforcement learning problem with horizon equal to 1. Okay? So there is also a series of recent papers on contextual decision process, which also assumes black box access to general function approximators. All right, so a lot of this previous work, they focus on the so-called model-free setting, in a sense that you're trying to directly learn the Q function or the optimal policy of your problem by just directly interacting with the environment. Okay? But if you look at a lot of practical reinforcement learning papers, they often have something different. So often they say that a model-based approach, which is something that you use data-driven approach to fit a Markov transition model and then plan from it, is much more sample efficient than model-free ones. All right, but except those empirical results, they don't provide any theoretical justification for that, right? So in this paper, we try to give a formal study of this comparison, model-based versus model-free. And we're also going to provide a pack model-based algorithm that is general enough to solve a large family of Markov decision process. All right, so let me describe the setup of model-based RL. So we're going to assume that we have some true underlying dynamics, right, P star. And because it's unknown, so we're going to use a set of function approximators to capture it, right? So here you should think about this function approximator as some conditional distribution that maps state action pair to some distribution at next time step, okay? We're going to assume realizability. And the second assumption that we're going to have is a black box access to some planning oracle, which takes an arbitrary model, a reward as input, and output policy that optimizes the reward under the given model P, all right? Now, what about the definition of model-free algorithm? All right, so we looked into the literature and we tried really hard to find one, but unfortunately we couldn't really find one, at least one that is general enough, right? So then, we basically tried different stuff, and finally we reached to the following definition. Let me tell you this and see if you agree with it, okay? So similar to model-based approach, we're going to assume that this model-free method also has access to some function approximators. But here you should think about this function approximator as a function that is trying to approximate the underlying value function or the underlying optimal policy, okay? And let's revisit this picture, right? So agent sends action, and then environment reviews the next state, all right? So here, instead of letting this environment review the state, we're only going to allow this environment to review the so-called Q profile, which is a vector that consists of values from your function approximator, your Q function approximators, a value at this particular state X. Okay, so you could think about this as some featureization of the state, right? The featureization is determined by your function approximators. Okay, Now, this is definitely not the only definition. You probably can come up with some other definition that can work, but what we found is that it actually is pretty general in a sense that it captures a lot of existing no-pack reinforcement learning algorithms, such as efficient Q-learning, fitted Q iteration, more recent work such as Olive, and even policy gradient-based method. Right? Now, so intuitively, when your function class is restricted, this Q profile actually potentially will exclude information from your state, right? Which causes partial observability. And it is actually this partial observability that leads to the following separation result. So we can show that there exists a family of Markov decision process, such that to learn the new optimal policy, there is a model-based approach that can spend time polynomially with respect to all the relevant parameters that you care about. But for any model-free method that falls into our definition, has to spend time at least exponentially with respect to the horizon of the problem, right? So such kind of exponential separation potentially indicates the benefit of model-based methods, right? Indeed, if you look into the literature, there are actually a lot of pack model-based reinforcement learning methods that were designed for special, MDPs, right? But our question here is that, can you design a unified algorithm that potentially could work for all these environments simultaneously, right? Including some environments that I didn't put into this slide. And the answer is yes. So let me introduce you this metric, which we call it witness rank. So intuitively, you should think about this metric as something that indicates, the hardness result of your MDP, the hardness of your MDP, okay? So let me describe this misfit matrix, of which the size is number of models times number of models. For a particular entry in this matrix, which is indexed by the row model and a column model, we're going to use this row model's optimal policy to provide a state action distribution in the real system. Right, then conditional on this distribution, you can compare this column model, this PC, against the real world model, right? Using a set of test functions, or you can call it discriminators if you want, right? So basically, this is an integral probability metric that's trying to measure the transition between, the difference of the transition between your candidate model and the real world model, okay? So if this number is non-zero, then your model is not going to be the real world model, okay? We're going to define the witness rank as the rank of this matrix, okay? Now, I promise you that this is not some crazy metric, we come up randomly, right? It is actually pretty general in a sense that it captures a lot of complexities that people previously developed for designing specialized algorithms for a lot of different reinforcement learning problems, right? And what's more, we can actually use that to design a unified algorithm that can achieve sample efficiency for all these environments. And I'm not going into details of the algorithm, but in terms of the result, we can show that the sample complexity scales polynomially with respect to the relevant parameters that you care about, including a quadratic dependency on the witness rank. But more importantly, there's no explicit poly dependency on the number of states, right, in this expression. And instead, we have this statistical complexity of our model class and the discriminator class, the test function class, okay? So the take-home message is basically, model-based RL with general function approximation could be exponentially more sample efficient than model-free ones, okay? And then in model-based RL setting, sample efficiency is possible when the witness rank is small. And we showed for a lot of existing problems that are pack learnable, the witness rank is actually very small. So that's it, thank you. No. Our lower bound is only linear with respect to the rank, so I think there's some gap. Yeah.
So I have a question regarding your formulation of model-free
Yeah.
methods. So there the assumption that you make is that the optimal Q function is in the class.
Yes.
But you also assume that the Q functions of all the possible policies lie in the class.
The Q functions of all the
Do you
possible.
think that this negative result would still hold if all of the Q functions of all of the policies that you could use would lie in the class?
All the policies. So we start from a set of Q functions, right?
Yeah.
So I don't. What do you mean by the policy?
Yeah, so if you make a stronger assumption about the set of Q functions, can you avoid this negative result?
Probably, yeah. So if you increase the richness of your Q function class, right, you potentially will identify, the state again. At that case, there's no information loss. Then, yeah.
Okay.
Oh. All right. Thanks.
Thank you. All right, so let's go back to